Hi, everybody. I just wanted to make a quick video for you. I say quick, but I'm never all that quick, to talk about drag forces and how they relate to what you actually need to know about drag for AP Physics 1. Um, First off, what is drag? We use this term drag, air drag, water drag. What is it and what causes it? Well, drag, first off, is a resistive force, meaning it is always trying to resist the motion of an object through something, in this case, through a fluid. Resistive force acting on an object as it moves through a fluid. Now, when I say fluid, I don't necessarily mean a liquid because anything that's non-solid is technically considered to be a fluid. So, air drag would be the resistive force that air exerts on an object. You could have water drag, that would be the resistive force that water exerts on an object as it moves through, like on a boat hull or something like that. But any fluid is going to exert some resistive force on objects that go through it. Now, why is this? What causes it? Well, think about this. Let's say you have a ball, and let's say that ball is moving this way. It's got some velocity in that direction. Well, that ball, in order to move through the air, has to collide with all of these little microscopic invisible air particles, whatever they are. And in order for these particles to get shoved out of the way by the ball, because it's not like they can go through the ball has to exert a force on the air particles. It has to push them this way. So Newton's third law says if the ball is pushing the air particles this way, then the air particles are going to push the ball back that way. That collective push of these particles in this direction is what we call drag. And it doesn't just come from air. If this were trying to go through water, there would be a drag force on it from all of the water particles. So it's all of these small particles pushing against the object that is pushing through them that we call drag. What are the factors that affect the amount of drag? Well, let's talk about the obvious one first. The speed of the object. I think you can probably understand that if this object were going very slowly through the air, it's not running into very many of these air particles, and it's going to experience a much lower drag force than if it were moving fast. So faster equals more drag. Number two, the shape of the object. This has got kind of a rounded front surface. It's a ball. Well, what if this were like a coffee can, a cylinder that we're moving through the air? Well, this is actually going to experience a greater drag, assuming everything else is kind of held constant here. Let's say this were a coffee can with the same diameter as this ball. This coffee can is actually going to experience a bigger amount of drag than this ball would, even if they're at the same speed. So the shape of the object, the more aerodynamic, I guess you could say, the lower the drag. The more streamlined it is, the lower the drag. As you'd expect, a blunt object is going to get more drag. So the speed of the object, the shape of the object, the type of fluid. You're going to get more drag out of water at any given speed than you are out of air at that same exact speed. So the type of the fluid, the density of the fluid, literally what is the fluid made of, all of those things kind of matter. And finally, this is also a biggie, the size. And when I say size, I'm actually talking the cross-sectional area of an object. So let's go back up here to our ball. If I take that ball chop it right down the middle, and then I sort of look at the end that I've just chopped, the area at the biggest part of the object is called the cross-sectional area. That's what I'm talking about here. So the bigger the cross-sectional area of the object, the more drag it's going to experience. Makes sense. It's going to hit more air. So these are the four main factors that affect how much drag an object has on it. As far as an equation, well, this drag force, like I said, the direction is always going to be opposite the direction of the object through the fluid. It's a quadratic equation, actually. It's got two terms. The first term depends on the speed of the object, v, and the second term depends on the square of the speed of the object. Now, let's look at this equation. The force, the drag force, which would be measured in newtons, has to be equal to these two terms added up. So these, C1 and C2, these are experimentally determined constants. And they depend on, oops, not the speed. Let's check the wrong one off here. They depend on the shape of the object, the type of fluid that the object is going through, and the cross-sectional area of the object. That's what C1 and C2 depend on. They're constants. You would have to figure them out by doing an experiment. The speed comes in V here. Now these constants would have to have units that would give you newtons if you were to plug in a speed or a speed squared. So the units for C1 are always newtons per meter per second. That way the meters per second cancels with the meters per second there, giving you newtons. And the units for C2 are always newtons per meter squared per second squared, because they have to cancel with meters squared per second squared to give you newtons. Now the nice thing is you don't really have to do much with this equation in AP Physics. You just have to understand kind of the basics of how drag works and the factors that do affect the amount of drag. These are pretty intuitive, so the things that you have to do with drag in AP Physics aren't very big. Now, for some objects, this term, the constant C1, is much larger than the constant of C2. So for some objects, this whole term right here doesn't matter too much. So that means that drag is directly proportional to how fast the object is moving through the fluid. For other objects, this constant is much greater than this constant, so this term doesn't matter too much. And for those objects, the force that drag exerts is actually proportional to the square of the speed. So like doubling the speed would more than just double the drag, it would quadruple the drag. So without knowing what these constants are, you would never know what doubling the speed would do to this drag force. So you don't have to do a whole lot with this equation in AP Physics. Just understand that these are the factors that affect the amount of drag, and that the direction of the drag force is always opposite the direction of motion. I'll give you an example of how you might be asked to, kind of qualitative questions here. Top speed of an automobile. Why do automobiles eventually reach a top speed? Now let's say you got a car, and all my cars look like Volvos. They're boxy. So you got this car, and this car is moving this way. It's moving to the right. Well, the air drag, since we're running into the air here that's in front of the car, the air drag is going to be pushing back to the left on the car. Now let's say this car is trying to accelerate. So if we looked at a schema of what the forces acting on the car would look like, car, that would have to be in a bubble. The road, that's a relevant object, that would have to be in the bubble. The entire Earth, that would have to be in a bubble. And since air drag is obviously an issue with a car that's trying to go fast, air is going to be in a bubble. Now, I can't think of any other objects that are touching my car, so The road actually exerts a normal force and a friction force on the car. The air exerts a drag force, and the earth exerts a long-range gravitational force on the car. So if I were to diagram the forces acting on my car and make the car my system, I've got 1, 2, 3, 4 external forces acting on the car. So I'd have the Earth's pull, that's this one, mg. I would have the road's normal force. I have air drag opposing the motion of the car. And I have the friction from the road. Now, people think, well, friction from the road, that would oppose the motion. Well, not in this case, you guys. Let's stop and think about this. These wheels are getting turned by the engine like this. Those wheels are touching the road, so they are literally shoving backwards on the road. So if the wheels shove back on the road, that must mean that the road shoves forwards on the wheels. And that's friction that does that. If you don't believe me, go find a nice patch of ice this winter and floor it. See, without friction, how well you can accelerate. So this is actually the force of friction that causes a car to accelerate in the first place. Friction between the road and the tires. Now, as long as these two forces right here, I don't think we have to worry about vertical. Those are balanced. As long as these two forces are unbalanced, this thing is going to accelerate. So if this thing is going slow, the sum of the forces in the x direction would be the friction force minus the drag force. And Newton's second law says that would have to be equal to the car's mass times its horizontal acceleration. So if FF is bigger than FD, this is non-zero. That means the acceleration is going to be non-zero. But here's the weird thing. Let's go back. Remember the factors that influence how much drag there is. Let's say that this car, due to this setup, accelerates. It goes faster. Well, maybe after it goes a little bit faster, the forces now look like this. So the car, the friction from the road is still pushing the car forwards. But now that the thing is going faster, we know that the speed of the object affects the amount of drag that the object has. So once the thing is going faster, now the drag force is bigger. Well, there's less unbalanced force now because these two are closer to being the same size. So that means the acceleration is going to be less. What about when the object goes even faster and there's even more drag? You can probably imagine eventually you're going to reach a situation where the drag force becomes just as large as the road pushing the car forward. And when this and this become the exact same size, there is no more unbalanced force, therefore no more acceleration. We call that the car's top speed. That's why a car goes to some top speed and can't go any faster. So if you're an automobile manufacturer, if you're designing cars, a way that you can actually help a car without even messing with the engine or anything, you can help a car have a higher top speed. Let's look back here. At any given speed, what are the things that affect the amount of drag? Well, shape. Yeah, if you're a car designer, you can change the shape of it. You can't really change the fact that you're moving through air. And you could change the cross-sectional area of a car. So think about cars that have a high top speed, a Corvette, a Ferrari, something like that. Very, very aerodynamic shape, and they're not big. If you look at the cross-sectional area, it's actually really, really small. or look at like a Formula One car, something like that. They try to reduce these to make these drag coefficients as small as possible. And in doing so, they actually allow it to get to a higher top speed before the drag becomes as big as the cars, the road pushing the car forward. Another example I have for you. Let's talk skydivers. So let's say that somebody jumps out of an airplane. Forget about the fact that they're moving sideways when they jump out. Let's just talk about their vertical motion. Maybe they hopped out of a helicopter or something just to make life easy. So you got this person, and they are plummeting through the air. So as far as the forces acting on them, I'm not going to make a schema here. You're going to have the downwards pull of the earth on them. Remember, they're moving through the air this way. But due to the fact that they are shoving air particles out of the way, they are going to have a drag force acting on them. Well, a sum of the forces in the vertical direction on these people, this statement would say drag minus weight, mg is the weight, that's going to equal their vertical acceleration. So let's say you have just jumped. You're not moving very fast yet, so you don't have a large drag force acting on you, but you do have a fairly large gravitational pull on you. In this case, this is larger than this. That's unbalanced, so you're going to have a negative or downwards acceleration. Now, the product of a negative or downwards acceleration when you're already moving downwards is to speed up. So at some later point in time, you've got a bigger speed downwards. Same person. You can imagine when you're going faster and faster, this drag force is going to become larger and larger. So you will eventually reach a point where your speed becomes fast enough to where the drag force becomes large enough to where you don't speed up anymore. Once these two forces are balanced, you are no longer going to accelerate. If that and that are the same size, acceleration has to be zero. What's that mean? You stop? No. That means you stop speeding up. You stop changing the way that you move. You have reached, kind of like with our car, you have reached a top speed, but we don't call this top speed with somebody that's a skydiver. Typically, you call it the terminal speed. And terminal speed happens for a skydiver, or any object falling through the air for that matter, happens when the drag forces are equal in size to the object's weight. That's what causes an object to stop speeding up. You guys know skydivers don't just keep going at terminal speed till they hit the ground. They would all die. So what do? You pull the cord. You're moving down really fast, and all of a sudden, big parachute. Now, you were at terminal speed, and you were at terminal speed because the forces acting on you were balanced. Now let's look at the forces. Your weight is still pulling down on you, but look at what you have changed. You have changed the shape of you. You haven't done anything to the type of fluid, and you have changed in a big way the cross-sectional area, because this thing has a huge cross-sectional area. Now what that means is the drag force now has become much larger than the earth pulling you down, than your weight. And when there is a large unbalanced force upwards on you, that's going to be a large upwards acceleration. This is huge. This is relatively small. You're going to have an upwards acceleration, meaning your velocity is going to get smaller and smaller. Now, eventually, once again, you're going to reach a situation where your speed has gone down as this parachute slows you. Your speed has gone down to the point where the drag force is equal to your weight again. But now you're going much, much slower in order for that to happen because of the uh, extra cross-sectional area and the fact that you've changed your shape drastically. And you're at terminal speed once again. Remember, terminal speed simply means that the drag force on you is equal to the Earth pulling down on you. You're at terminal speed once again, but it's at a much lower terminal speed now than it was before, thankfully, because this is a terminal speed that you can handle hitting the ground at. So terminal speed, you guys, you got to be kind of familiar with that term, terminal speed. You got to be kind of familiar with that, and it's simply terminal speed happens when the drag force acting on you is equal in size to the weight. And that means that you're not going to speed up or slow down anymore. And that's going to happen at a different speed depending on the size and shape of the thing falling through the air. Think about like a piece of paper. I drop a piece of paper, it's going to have a much lower terminal speed than if I drop like a BB or something like that, or a baseball. A baseball would have to go much, much faster before the drag on it became the same size as the gravitational pull on it. A piece of paper does not have to go very fast before the drag force is just as big as the weight of the paper. So hopefully this helps you kind of understand drag, what causes it. Remember, these are the causes and the factors that affect it, and kind of how it affects the motion of some everyday normal objects you'll encounter.